Hi, everyone. So throughout this course, we've talked a lot about climate models and projections of future warming from climate models, but I just want to be a bit more precise about what we mean when we talk about a climate model. So climate models are computational models of the Earth system, and they use physics equations to describe how the fluids on Earth's surface move heat around the Earth. So how the ocean and the atmosphere move around and how they move other tracers around as well. So these equations come from conservation of energy and from Newton's laws of motion for a fluid on a rotating sphere. So what the climate model does is it splits the Earth up into a bunch of different grid boxes, kind of like, you can think of it as like when you're looking at a map or a globe, there's lines of longitude and latitude. The model sort of does that, splits the Earth up into all these different boxes and then solves the equations within each box and steps forward in time, continuing to solve these equations and passing information from one box to the adjacent boxes. So climate models are very useful tools for making predictions about how Earth's climate will change going into the future. They're also equally as useful for just building a better understanding of how the climate system works. So for example, we looked at the IPCC figure of the different representative concentration pathways for different levels of CO2 emission scenarios. And so while there's only one Earth, we can only have one real emission scenario, but using a climate model, you can test the differences in the response of the Earth system to these different emission scenarios. So we have a couple Excel models that we will be using as simple climate models. And the first one is a one-layer ocean model. And this has all the basic essentials that we need for simulating global mean temperature change. It does an okay job, but it's not perfect because it only includes a shallow ocean mixed layer. It doesn't include the full depth of the ocean. So this is the equation that we use for the model. This is the only equation in that model. There's a mixed layer heat capacity for the ocean. And then there's this lambda T term, which is the radiative response of the mixed layer. And then there's this R term, which is the radiative forcing. So the radiative forcing is the combined incoming solar radiation, as well as the downwelling long wave radiation, which is absorbed and re-emitted by the greenhouse gases in the atmosphere down to the surface. That warms the ocean mixed layer, and that warming is modified by the mixed layer heat capacity. And then the ocean mixed layer has this radiative response. So it warms up and thus its temperature changes, and its temperature response is modified by this lambda term, which is a feedback parameter. So it encapsulates all of the climate feedbacks in this system. So a little bit more about climate feedbacks. So feedbacks are both in climate and in electrical engineering are a process that make the forcing a function of the response. So what do I mean by that? I mean, there's some reference system and you force it with some sort of input of energy. The reference system then responds with some kind of response. Maybe it's an output of energy. When there's a feedback, the response, part of the response feeds back and modifies the forcing. So the reference system will have some response. Part of that response comes and changes the forcing on the reference system. Another model that we have is a two-layer ocean model. So this two-layer model does a much better job of capturing the climate response because it actually includes the full depth of the ocean. So we still have this radiative forcing component. We still have the ocean mix layer, and we still have this radiative response. But now we have an extra term, which is the heat transport from the ocean mix layer. As it warms up, it can transport heat down to the deep ocean. Okay, so how does that change our equations? So now we have two equations because we have two layers. This is the same. We still have this mixed layer heat capacity and this change in temperature with time term. We still have this lambda T and radiative response and this radiative forcing, but now we have this beta term, and that is representing how much heat is transported from the mixed layer to the deep ocean. And another thing that governs that heat transport is the temperature difference. So the temperature of the deep minus the temperature of the surface. And then the change in temperature of the deep ocean is governed by this equation here. So the deep ocean heat capacity, and then this beta heat transport term, and then the temperature of the surface minus the temperature of the deep ocean. The deep ocean has a bigger heat capacity because it is a much bigger volume of water than the ocean mixed layer. And then just a quick word about aerosols, because in the Excel model available in the files section of the Canvas page, there's an aerosol scale factor, and you can play around with that. But aerosols are one big source of uncertainty when it comes to projecting future temperature change, because aerosols have various impacts on the temperature response of the Earth system. So whether or not they're a positive or a negative feedback is a bit uncertain. And there's also a lot of different kinds of aerosols. So aerosols are basically just any suspended particle in the air. There are naturally occurring ones like sea salt, dust, bacteria, volcano outgassing. And then there are also man-made aerosols like black carbon and pollution. But they have various impacts on the change in temperature, the response of the climate system. So I've talked a bit about uncertainty when it comes to climate models. So how do we validate models? There is uncertainty, but how do we say, okay, this model is doing a good job and we can trust that we know the physics and we know that this is a pretty good projection of future warming. So there's these parameters that we can kind of tune in models, like the lambda, the feedback parameter, and the aerosol scale factor. But it's not just about tuning the model to get your temperature record to match observations. So there is a bit of that, but there's also a lot of ways that we can look at the output of the model to make sure that it does a good job. So we can look at and see if it reproduces historical global mean temperature record that we have. We can also look at whether or not the models can reproduce cooling that occurs after a large volcanic eruption, whether or not we can reproduce the last ice age conditions. And then there's also, beyond just global mean temperature, there's looking at, does the model do a good job of reproducing the ocean circulation, the atmospheric circulation, the heat transport that's done by the atmosphere and the ocean. We can also look at sea ice extent and thickness and see if the models do a good job there. There are a lot of cloud properties that we look at. Clouds are notoriously difficult to model. They have a lot of really complicated physics going on in them. So does the model do a good job of putting the right kinds of clouds in the right places? So there's a lot of different things that we look at, and it's more than just looking at reproducing the historical global mean temperature record, though that's very important. That's it for this video. Take a look at the Excel model, so go ahead and download those, as well as the handouts for the Excel models. Work through those exercises and play around with the models to try and understand what happens when you change the feedback parameter, what happens when you increase it or decrease it, and what happens when you change the aerosol scale factor as well.